Welcome back to learning about how to do measurements. So we've talked about what a measurement is. It's a number with a unit. We talked about scientific notation, how we have to measure big and small things in science, and we've talked about accuracy and precision. Now we're going to talk about taking actual measurements and how we report the measurements based on our equipment. So some books call it significant digits, some significant figures. I'll usually say sig figs because there's too many syllables there. So sig fig in a measurement, they include all the digits that we know with certainty, and those are the ones that have been marked or you have lines on your measuring device, whether it's a ruler, a thermometer, whatever it is. And you get one more digit that's an estimate. To your best ability, you read between the lines. You guess, you mentally subdivide it into 10 parts, and then decide where the line should be. When you're measuring, if you're exactly on the 12 centimeter line, then you're going to add at least one more zero. Okay, if you're at 12.1 on our particular rulers, then you're going to add a zero, 12.10, and you would have 4 significant digits. But those darn zeros, especially at the end, are tricky. So here's a terrible ruler, absolutely ridiculous. Nobody would have a ruler like this. But from end to end, it's a 1 meter. Anything in between is a guess. You don't know where it is. It's a guess. So you know it's more than 0 and it's less than 1, so mentally divvy it up, divide it up. I mentally kind of go, oh, that's about halfway. And what the book says is that's 0.6, 6/10 of a meter. If you had a little bit better ruler, which still isn't great, it would be marked off every 10 centimeters. Remember, a meter has 100 centimeters. Centi's a hundredth, like a penny is a hundredth of a dollar. So when we put our piece of wood on this ruler, we see it's definitely more than 60, way less than 70. Mental math, you might argue back and forth that you could see that as 62. Meh. They called it 61 centimeters, which is 0.61 meters. We go from 1 significant figure to 2 now. If we get a normal looking meter stick, we actually have individual centimeters marked, and we can see with certainty that this piece of wood is past the 60, but not quite to the 61. At least I don't think so. It's closer to 61. So what they did is they said, that's about 7/10 of the way. You might go, I think it's 8/10 of the way. That's fine. That last digit is a little uncertain. Depends on your angle and parallax and all that kind of stuff. But it is still significant. Because I know for sure it's not a 1 here, okay, or a 2. All right, let's look at a make-believe beaker. Now, beakers are really bad for measuring volume anyway because they're just guesstimates. They're just stamped on the side. They're not very precisely incremented. But this is 20 and this is 40. That must mean this is 30. So if this is 40 and that's 60, that's 50. It's definitely below the 50 milliliter line. Okay, so 1/10 of the way between there is about 1 milliliter. So I would call this 47 milliliters. I don't get to add a 0. I don't get to add a decimal with a 0 because I don't have marks here to indicate that I would know that with any certainty. 2 sig figs. Here's the graduated cylinder. You probably know that you read the bottom of the meniscus. So this line across is 35. This line across is 40. There's 5 spaces in between. That means these are 1 milliliter lines. Halfway between 36 and 37 is what it looks like to me. So I know for sure the 30 and the 6, for sure it's past that. For sure it's not at 37. It's somewhere in between. You might decide it's 0.4, that's fine. but I get 3 sig figs in this measurement. On the other hand, if you use a burette tube, those long skinny tubes, and they read weird. You'll notice that the bigger numbers on the bottom because you're usually using gravity feed to drain them. But here's 20. There's a middle point, and here's 21. There's 10 spaces in between. Each one of these is a tenth of a milliliter. So it's 20.1, 20.2, 20.3, definitely more than 20.3, not quite 20.4, definitely not 20.5. So this could be reported as 20, for sure you know that, 3, for sure you know that, and then best guess, 8. Remember, 38 is closer to 40, right? It's close to this 4/10, but not quite there. So this one had 4 sig figs. Obviously, the more significant digits, the better. The more confidence you can have, the more repeatability you can have. So that's why sometimes when we talk about precision, it's not just repeatability, it's also how finely gradated your instrument is. When you're reporting measurements, you want as many digits as you possibly can, because usually you're going to do some sort of calculation with those measurements, whether you're multiplying, dividing, adding, subtracting, and in that process, you have to be careful with your significant digits when you report your final answer. So on the pages in your book, I asked you to write down the first line of each of these rules. Every digit that's not 0 is significant, always. If there's a 0 in between 2 other non-zero digits, they're always significant. I call them sandwiched zeros, like here. Zeros out in the front before there's any non-zero digit are just placeholders. So on really tiny numbers, like 0.0071, these 3 zeros are just to tell you this is a small number. They don't tell you anything more than that, and so you don't count them as significant. Okay? Zeros at the end and to the right of a decimal point. Okay? The end of a number and to the right of a decimal point after, as long as there's a non-zero digit in front of it or somewhere in here, any zeros after that are significant. Okay, so 43.00 has 4, 1.010 also has 4. This 0 is significant. These 2 zeros are significant. This tells me that it's somewhere between, it says meters, but let's use dollars, right? $43 is how you would read that. 43.01, one more penny, or 42.99. That's the possible range. This last digit's uncertain slightly, not in the normal sense of the word, but in the measurement sense of the word. All the others are absolute. Zeros at the right end of a really big measurement, like how many stars there are in the universe. Okay, if there's no decimal place, which there usually won't be, they're not significant. Finally, if you're doing any kind of calculations or, conversions between like 60 minutes per 1 hour, the 1 hour isn't one significant digit. It gives you whatever the next number you're dividing into it has as the fewest. And that'll make more sense in a minute. So, again, 1 sig fig, this one can have 2, and this one can have 3. How many sig figs in 123 meters? Hopefully you got 3. How many, so I think I go down on this. So 9.8000 times 10 to the 4th actually has 5. All those zeros are significant. They're after a non-zero digit that has a decimal also. So they count. Going down again, 0.07080. That only has 4. These front zeros without a 1, 2, 3, 4, 5, 6, 7, 8, 9 in front of it are not significant. So they're just placeholders telling you how small. The better way to write this so there's no confusion would be to change it to scientific notation. 40,506. Hopefully you guessed 5. anything that has an absolute count, if you're counting people, counting meter sticks, counting pencils, whatever it is, those are technically unlimited. 98,000 meters only has 2. Hope you did well. And these are the explanations if you want to go back and read them on the previous slide. All right, try these. And again, go back and look at the rules if you're not sure. We can talk about it more on Thursday as well. Okay, so doing calculations with sig figs is a little bit tricky. If you're adding together numbers, you're multiplying numbers, you're dividing numbers, you can't get more precision in your measurement. You are limited to the worst instrument that's used. Okay, everybody has the same graduated cylinder, same meter stick, whatever. It doesn't matter, but sometimes you have better, more precision in your instrument, and you can't get more precision in your measurement because you did a calculation. One of the weirdest things that that we do in here is rounding, and people get all crazy. This is just as simple as you remember from grammar school. You always start on the right-hand side of a number and work your way to the left when you round to significant digits. Remember that. You actually have to decide how many sig figs you're allowed to have in your answer. I always just run all the numbers through my calculator and then round at the end. So, for rounding, if the number ends with a 1, 2, 3, or 4, and you're not allowed to have that last place, I say you round down. You round off is what you learned it as. If a number ends with a 6, 7, 8, or 9, you probably remember, like, there's a 4 here in front of the 6, and you have to get rid of the 6. The 4 becomes a 5. Okay? There's a 6 in front of the 7. The 6 becomes a 7, etc. Okay? So you round up. So that's easy, right? And if you look, there's 4 digits that go down. There's 4 digits that go up. One of the weird things is in science, when you were dealing with piles of data, there's this argument about what do you do with 5s? Probably all your life you've learned that a 5 makes the number in front of it increase if you're rounding it off, right? It's halfway to the next spot. There's, yeah, it's probably more confusing than it needs to be. But if you look, there's 4 that go down, 4 that go up. If we always go up with 5s, if we always round whatever's in front of the 5 to the next higher, you're going to skew your data ever so slightly up. Is it a big deal most of the time? Absolutely not. Okay? But you may see this when you encounter rounding if you get into any research. Okay, so if we always round it up again, the 5 would always make things higher. The way that I was taught in graduate school is if the number in front of the 5, again, normally you round up, but the little trick that I was taught by my graduate professor was odds up, evens off. So if our 5-digit number has to get rounded to 4 sig figs, if there's a 5 at the end and an even number 4 in front of it, we ignore the 5. If there's an odd number in front of it, we raise that odd number up. Remember, that last digit's always uncertain anyway. You might have measured it a little high anyway, or maybe a little low, hard to say. But odds up, evens off is a trick that I learned. I'm not going to beat that into you, but I just wanted to mention it for those of you going on in science. And again, the last digit is always a little bit uncertain. And this only applies to fives. And if you just round up fives all the time for our work in here, you're going to be fine. Okay, it's not a big deal. So when you're talking about lots of data and research. So low numbers, drop them off. Higher numbers, raise up. The last one. Okay. All right, so this one's supposed to be rounding to 3 sig figs. Hopefully you got that. This one also to 3 sig figs. Okay, the 1's low, it goes away. The 2's low, it goes away. Remember, these zeros don't count. 2 drops off. And this one's a little trickier. Okay, 3 sig figs. If you change it into scientific notation, it's a lot easier to see. Remember, this 0 on this number right here is not significant because there's no decimal. Only these 3 digits are. This 7 makes this 7 and 8, which makes this 7 and 8. And then if we do our little 5, what do you do with the 5? Well, the 5 makes that a 6. That makes that 10. Uh-oh. That makes it 630. The only way to report that accurately would be with a decimal, but that looks really dumb. So putting it in scientific notation takes care of that problem. When you add and subtract, you have to round to the same number of decimal places in the measurement that has the fewest digits after the decimal. So you add everything up, all the measurements you have, all the decimal places you have. You add them all together. So just like in grammar school, line up your decimals. And then because this one only has 1 place after the decimal, your answer has to be rounded. Okay? And so that 369.76 becomes 369.8. This one has 1, this one has 2, this one has 1. Hopefully you can figure out you should only have 1 place after. This has 2, this has 2. You're allowed 2 places after. This has 2, this has 2. You're again allowed 2 places after. 2 and 1, only 1 place after. You have to, well, the rounding doesn't do much here anyway, but you would have to round. Okay. Again, 1 place, 2 places, 3 places. You're only allowed to have 1 after the decimal. So even though your calculator spits out this, you're going to report it as this. For multiplying and dividing, you're going to use the measurement that has the fewest total sig figs. Okay? The actual decimal placing doesn't matter for multiplication and division, but you get the fewest total. So this one has 2, this one has 3. Your answer has to round to 2. This one has 4, this one has 3. This is division. Your answer is only allowed to have 3. This one has 3, this one, this is a conversion. So this is the definition. 1 minute is 60 seconds. So you're allowed whatever this number has, which is 3. Your calculator is going to spit out this craziness, but you have to go to 3. Okay, you're following a volume, length times width times height. 3, 3, 2. Calculator is going to give you a big crazy number. You're only allowed to have 2 digits, significant digits in your answer. And of course, you need to report it with the volume units, meters cubed. Okay, that's it for today. I hope that was helpful. Take care.